Here's another example we can try. Let's start by looking at our given information. So we'll read through the problem and summarize what we have here. 2 kilograms of water contained in a piston cylinder device begins as a saturated vapor at 320 degrees C. So lots of information in there. First thing to realize is this is a closed system problem because our system is just a little piston cylinder device. So inside of here we have 2 kilograms of water, closed system. Also in that first sentence we know T1 is 320 degrees C and it's a saturated vapor. So that fixes the state, as we'll see in a moment. Back to the problem statement, it undergoes 3 processes to form a cycle. So let's look at those 3 processes and describe what we can about them. First one, a constant temperature expansion until the volume is doubled. So 1 to 2 is constant T, and also V2 equals 2 V1. 2 to 3, in other words, the second process, is constant pressure process. So that's all we know about that, is it's constant pressure. And finally, constant volume. So 3 back to 1. Notice this is a cycle, so it ends up back at the same point as it started. So we use state point 1 as the end of this last process. And that's constant volume. Also given in this problem is the net heat transfer. So let's just put that over here. Q net is equal to 53.65 kilojoules. Notice it's a total amount in kilojoules, so I use a capital Q here, Q net. Calculate the work and heat transfer in kilojoules for each of the 3 processes. So that's what we've been asked to find. So we'll write that down here. So what we're asked to find is Q and W for each process. Begin with a list of assumptions. Many of these problems we would build the list of assumptions as we go along. This one we'll try and put down some assumptions that we're quite sure we're going to have to make. First of all, it's a closed system. So this piston cylinder device isn't leaking or anything like that. There's no inlets or exits. So we assume it's a closed system. We're going to be using the first law here certainly because we need to calculate heat transfer, and we'll be assuming that kinetic energy and potential energy are negligible. And that's what makes the right-hand side of the first law delta U instead of the more general delta E. We're also going to be doing work calculations which involve integrating PDV, so we'll put this down right away as well. Quasi-equilibrium process. So work is equal to integral PDV, which we'll be using. Certainly needs that assumption tagged onto it. So in this case we're able to write down the assumptions because we can sort of look ahead and see what we're going to be doing. If you're not confident doing that, just leave the assumption list blank, but make sure you go back and add things to it as you make the assumptions later on. So in this solution we're now ready for the analysis. So remember what we're asked to find: heat transfer and work transfer for each of the 3 processes. Well, as with many of these problems where we're calculating work, I think it's quite helpful to draw a PV diagram. So notice we weren't asked to draw a PV diagram, but it still can really help us out with these solutions. Now the first thing we need to remember in this case, our working substance is water, and it's likely undergoing a change in phase. So we want to make sure we show the saturated liquid, saturated vapor lines on there. Now we take a look at our state points. Remember, the first point was described as being on the saturated vapor line. So I'll put my first point right there. The first process is a constant temperature process, so I'm going to draw a line of constant temperature just as a dashed line for now through that point. So this is the 320 degree isotherm. So everywhere on that line is 320 degrees C. If we go back up to the problem statement, remember that from 1 to 2 is constant temperature and the volume doubles. So we know we're going through an expansion. So I'll actually fill that in solid down to, say, there. So that's point 1 and that's point 2. Now this isn't a straight line, it's just a sketch. It's a curved line of some kind. So that gets us to point 2. 2 to 3 is a constant pressure process, so that's a horizontal line. And 3 to 1 is constant volume. Now if this is going to complete a cycle, which it should, it means the constant pressure process must come back this way. So point 3 is there, and the constant volume process straight up to the final point, point 1. So we're going around this little cycle in a clockwise direction. So that's our PV diagram, and that'll really help us, I think, calculating work and heat transfer later on. Now, let's tackle these processes one at a time. So we're going to start with process 1 to 2. Just want to change back to blue here. So 1 to 2. First law tells us that Q minus W from 1 to 2 is the change in internal energy. So Q minus W equals delta U, but here I've written it in terms of the process from state point 1 to state point 2. What do we know about point 1? Well, T1 is 320 degrees C, and it's a saturated vapor. So that's enough information to fix state 1. So we go to table A2, and from that information we just simply look up U1, so the internal energy, 2525.5 kilojoules per kilogram. And while we're there, look up the volume as well, because we're going to need it for work calculations here eventually. It is 0.01549, and that's meters cubed per kilogram. So these two things are coming from table A2, saturated vapor values at 320 degrees C. State point 2, what do we know about state point 2? Well, it's a constant temperature process from 1 to 2, so T2 equals T1 is that same 320 degrees C. So that's one property at point 2. The other property we know is that the volume doubles. So V2 is double V1, which makes it 0.03098 meters cubed per kilogram. So these are the 2 points that we know at state point 2. And from our diagram, from our PV diagram, we know that these are in the superheated region, so we know we have to go to table A4. So going to table A4 with the temperature and a specific volume, we can look up the value of U2, which we need, and it turns out to be 2682.7 kilojoules per kilogram. And of course you're going to have to interpolate to find that number. And also interpolating, the pressure at point 2 works out to 73.03 bar. So these two numbers are coming from the superheated table A4 in your textbook. So if we take a look and just review where we're at here, just rewrite the first law for this process, 1 to 2. We now know the internal energy at 1 and the internal energy at 2, and of course we know the mass. So these two numbers we know, but we don't know either the heat transfer or the work transfer yet, so we can't solve for the other one using this. Now the only choice we have for getting heat transfer is this equation. So that means we need to find the work from somewhere else so that we can come back, use this equation to get the heat transfer. Well, luckily we do have a direct means to calculate work. So the work from 1 to 2 is equal to the integral from 1 to 2 of P dV, as we've seen before. Now, whenever we go to do a work calculation using this, we need to ask ourselves, do we know how P is related to V? In other words, do we know the path on the PV diagram? Because if we're going to calculate the area under this curve, we need to know where it goes. Well, in this situation, if we just recap what our PV diagram looks like, we're working with water, starting off as a saturated vapor, heading down a line of constant temperature to some other point. The problem we have right now, we don't have an equation that describes this line. Now, the way we overcame this in the past on a recent assignment was we went into the property tables for water, and we found points along there, and then joined them with straight lines essentially, and calculated the area of each of these trapezoids and added them all up. Now, on that assignment question, that was quite straightforward, simply because this end point here was really quite close to the beginning point, so I think there was only one of these trapezoids that we had to calculate the area of, so that was quite easy. Now, if you look at the conditions in this problem, and you look in the property tables, I think you'll find there's 3 or 4 points along here. So that would be rather tedious to calculate the area of all those trapezoids. Now, it would certainly be acceptable, and you could certainly go that route, but there's a lot of number crunching involved to do it. So that's not what we're going to do in this case. We're going to use an alternate approach, which only works here because of some other information we're given in the problem. So I just want to clean this up a little bit and talk about that. Remember, another piece of information we were given in this problem is the net heat transfer. Well, the net heat transfer for any cycle is equal to the net work. So if we can go to the other two processes and figure out the work for them, then we can come back and figure this work out from the net work. So that's what we're going to do. We're going to set this aside for a moment and look at the other two processes and see if we can't calculate this work from the net work and the work in the other two processes. So that means for now we move on to the process from 2 to 3. So again, first law from 2 to 3 is our starting point. Now this time we can go straight to a work calculation because we know the path. So the integral from 2 to 3 of P dV, this is the constant pressure process. So we just take the pressure at the beginning times V3 minus V2. And of course this only works out this way because that pressure is a constant. It can come outside the integral, and all we're integrating is dV. Now, we already know this pressure, that's 73.03 bar that we just found above. V2 we already know because it's just double V1, and I think we already wrote that down above. V3, of course, is equal to V1. So remember, V3 equals V1, and we know what that is. So we can go straight to this work calculation. We have all the numbers we need to put in there. Pressure, 7303 kilopascals. Notice I expressed this in kilopascals, not bar, so that the work comes out in kilojoules. Now these are capital V's. All I have available so far are specific volumes, so these need to be multiplied by the mass of 2 kilograms. So I'll put that out front, and then in parentheses we put our two volumes. So this is V1, which happens to be equal to V3, 0.1549, minus just double that, 0.03098. And those are both meters cubed per kilogram. And if we work that out, we get negative 226.25 kilojoules. And this makes sense that it's negative because we're moving from right to left on the PV diagram. So this is a compression, so the surroundings are doing work on the system. Now what I normally do is express the final answer to 3 significant figures. So this is 226 kilojoules. Now I keep this intermediate answer to more significant figures because we're going to be using it in later calculations and we don't want to lose precision. So that's our trip from 2 to 3 as far as the work goes. Now we still need to calculate Q, and in order to get Q we'll be going back to the first law, which means we need to get the internal energy at point 3. So that's what we move on to now, finding the internal energy at point 3. Well, the first thing we ask ourselves, what are 2 properties we know at point 3? And the 2 that we know are the pressure, because we know it's the same as point 2, so that's our 73.03 bar. And we also know the volume at 3, because it's equal to the volume at 1. We just used that in our work calculation. So those are the 2 properties we know. We also know that this is a mixture, and we can tell that very quickly just by looking at our PV diagram. We're underneath that initial point 1, which is on the saturated vapor line, so we must be in the mixture region. And since we know a pressure, the place we want to go is to table A3, the saturated pressure table. And we're interested in properties in that table that are at 73.03 bar. Now, since it's the volume that we know, we can use that volume to get the quality at this point. And in order to calculate the quality, we'll need a value of VF and VG at 73 bar. So we have to go into the tables and interpolate to 73.03 bar. And when we do that, we see VF is 1.3613 times 10 to the minus 3 meters cubed per kilogram, and VG 0.02620 meters cubed per kilogram. So from those we can get the quality. So the quality at point 3 would be V minus VF. So that would be V3 minus VF, because we're talking about the quality at point 3, divided by VG minus VF. And all of those numbers are available right here, and that works out to 0.5688. So now we have the quality, we can get internal energy, and again, because it's a mixture, we need UF and UG. UF is 1272.1 kilojoules per kilogram, and UG is 2577.3 kilojoules per kilogram. And so U3 will be UF plus the quality at 3, which we just got from the volume, times UG minus UF, which is equal to 2014.5 kilojoules per kilogram. So we'd have the internal energy at both ends of this process now, and we have the work. So back to our first law to get the heat transfer. So just rearranging that to move the work from 2 to 3 over to the right hand side. And we have everything we need to put numbers into that. So 2 kilograms times the change in specific internal energy. We just found this 2014.5, that's our U3. U1 we got a while ago, 2682.7. Both of those are kilojoules per kilogram. And then adding the work on, but of course the work is negative 226.25 kilojoules. And that works out to negative 1562.7 kilojoules. So we express that as a final answer to 3 significant figures, 1560 kilojoules. So that's looking at process 2 to 3. The constant pressure process, we calculate the work directly, and then we calculate heat transfer from the first law. Final process, 3 to 1. And so again, same starting point. First law from 3 to 1. Remember that the right-hand side of this is always the final internal energy minus the initial. We're going from 3 to 1, so it shows up in this order. Well, again, the work from 3 to 1 is 0 because it's a constant volume process. So that's straightforward. We already have done all the work to get the internal energy at the beginning and the end of this process, so we can go straight to our heat transfer calculation. Again, 2 kilograms is the mass times the change in internal energy. 2525.5 was our U1 minus 2014.5, those are U3 kilojoules per kilogram, and that works out to 1020.0 kilojoules. So just expressing that as our final answer, 1020 kilojoules. So that's 3 to 1. It's fairly straightforward because the work calculation is very simple. And also we already have the internal energy at both endpoints from our previous work. So all we need to do now is go back to our initial process from 1 to 2. And we already talked about how we're going to approach this. We recognize that the net work equals the net heat transfer. And of course that's going to equal the sum of the individual works for these 3 processes. And as we just found out, that's 0. So we can calculate the work from 1 to 2 from the net heat transfer, which we have, minus the work from 2 to 3. And so we can put numbers in there. 53.65 was given in the problem, kilojoules, minus, and the work from 2 to 3 was negative, 226.25 kilojoules. So this is equal to 279.9 kilojoules. So we found the work from 1 to 2 from the net work, and we express that as 280 kilojoules. And then finally, just back to the first law to get the heat transfer from 1 to 2. So we'll restate that here. And now we have all of these numbers from our previous work. So put those in. 2 kilograms still. U2 is 2682.7 minus 2525.5 kilojoules per kilogram plus 279.9 as our work. And that's already in kilojoules. So this works out to 594.3 kilojoules. So our final statement for Q from 1 to 2 is 594 kilojoules. And now we found the work and the heat transfer for all 3 of these processes. Notice that there's no rule that says that you need to find them in order. And this is a good example. It may be that you can find the work and heat transfer in the second process more easily and come back to the first one later on. That's certainly the case in this problem.